Welcome. In this video, we tackle day 2 of Unit 10, one-to-one functions and inverse functions, which are very, very closely related. This is section 6.2 from the book, One-to-One Functions, Inverse Functions, and we will hit all 4 objectives in this section. One-to-one functions. So what is a one-to-one function? Take a look at these two functions that are given in terms of arrow diagrams. In the first one, we have various states, and the function tells us, given a state, what is its population. In the second example, we have various animals, and given an animal, what is its life expectancy? Can you guess which one of these functions is one-to-one? Yes, it is the first one. The big difference is, in the second example, it's possible that you have two different inputs, like dog and cat, that lead to the same output, 11. However, in the first example, any two inputs that I take, like Indiana and South Dakota, must lead to different outputs, 6.7 and 0.9. This is the big idea behind a one-to-one function. A function is one-to-one if any two different inputs in the domain produce two different outputs in the range. How about functions that are given by formulas or by graphs? One of these functions is one-to-one, and the other one is not. Can you tell which is which? The one that's not is the one on the left, the x squared. This is f of x equals x squared. For example, if I plug in -1 for x, what I get out is a positive 1. So f of -1 equals 1. But if I plug in a positive 1, the answer I get out is also 1. f of 1 equals 1. So look at that. Two different inputs, -1 and 1, that produce the same output, 1. We say that -1 gets mapped to 1. 1 gets mapped to 1. On the right, this is my function g of x equals x cubed. Let's take a positive 1 as my output. Is there any x value that maps to positive 1? And the only thing that does is a 1 itself. How about a y value of 2? Is there any x value that maps to a y value of 2? Oh, yes, there is. In fact, that ends up being the cube root of 2. Going back to the first example, let me draw a horizontal line, I don't know, maybe at about a height 3. And I can ask, what are the x values that map to a y value of 3? And it looks like I have 2 of them. And we can see this because the graph crosses that horizontal line at 2 points. There's negative the square root of 3 and positive the square root of 3. So this horizontal line, the idea that a horizontal line cuts it in 2 places, definitely tells me that this function is not one-to-one. On the right, every horizontal line crosses at only 1 point on the graph. So for every y value, there's only one x that produces that y. So this is what leads us to the horizontal line test. If every horizontal line crosses the graph of f in at most 1 point, then f is one-to-one. The horizontal line test. Now we know the vertical line test. The vertical line test just tells us if a certain graph is actually the graph of a function. But the horizontal line test also tells us, is that function one-to-one? And finally, this brings us to the big idea, inverse functions. If f is a one-to-one function, then every element in the range corresponds to a unique element in the domain. Let's look back at this first example I had. Let's call this function f that maps states to populations. It turns out that since it's a function, of course, every element in the domain gets mapped to a unique element in the range. But in particular, this is invertible. There's a reverse function, f inverse, and every element in the range of f corresponds to a unique element in the domain of f, and we call that function that gives us that reverse correspondence, we call that the inverse of f, or we call it f inverse, and we denote it with an f superscript -1. So for example, the f function, the normal function, that might tell me that f of Oklahoma equals 3.9. But the f inverse function tells me that f inverse of 3.9 is Oklahoma. Think about domain and range. The domain of the f inverse function is the range of f. So looking at the f inverse, this is my domain here on the right. And then the f inverse takes everything in that blue set, its domain, and maps it to the left, becoming the range. So the domain of f inverse is the range of f. And also, the range of f inverse is the domain of f. So when comparing function f and function f inverse, they're very similar in terms of their domain and range, they just swap them. What does the graph of f inverse look like if I know the graph of f? So here's a function f that's been graphed, and we're going to go through the process of graphing its inverse function, f inverse. And we can start by looking at a few points. Here are some points that I know of this function. I know just by looking at the graph and seeing the lattice points that it goes through, f of 0 equals -7. Let me plot that on the graph. F of 0 equals -7. F of 1 equals 0. There's the point on the graph there. F of 2 equals 1, right there. F of 3 equals 2. Okay. Well, immediately, this tells me 4 points that are on my f inverse graph. Because look at this, let me go back up to the top. If I know that f of 0 is -7, then it has to be the case that f inverse of -7 equals 0. Because whatever the f function does, it maps 0 to -7. The f inverse function undoes. It maps -7 back to 0. All right, so f inverse of -7 is 0. I go to -7, I plot the point -7, 0, and this is a point on my f inverse graph. Next, f of 1 equals 0, so f inverse of 0 equals 1. I'll plot the point 0, 1. There it is. F of 2 equals 1, so f inverse of 1 equals 2. So I'll plot the point 1, 2. That's a point on my f inverse graph. And f of 3 equals 2, so f inverse of 2 equals 3. F inverse of 2 equals 3, 2, 3. Look what's going on here. There is an interesting symmetry. And if I graph this diagonal line that goes right through the origin, all the points on my original f graph are sort of reflected over that line to become points on my f inverse graph. And so in fact, the whole curve ends up getting reflected. So maybe it would end up looking something a little bit like this. There we go, and that's the graph of f inverse. So the graph of f inverse ends up looking like the graph of f is just reflected over this diagonal line, and that diagonal line is the line that has the equation y equals x. So here it is as an official statement: the graph of f inverse looks like the graph of f, but reflected over the line y equals x. And how you graph it is first plot a few points for f, and then plot a few points for f inverse, and then you can fill out the rest of the graph by being careful to take care of this symmetry. Let's verify that two functions are inverses. Let's say that I have functions f and g. How do I know if these two functions are inverses of each other? I can compose, let's say, f of g of x, and see if that equals x. Now, this has to be true for all x in the domain of g, which is basically all the things I can plug into that composition. And the other way around, g of f of x equals x. So the idea of this, imagine that there's an x just sitting there all by itself, not a care in the world. Along comes the function g, and g turns x into g of x, something else. But then along comes the function f, and if f takes that thing, what will happen? Well, remember, f and g are inverses of each other, so whatever g did to the x, the f will undo that so I should end up back at the x again. Similarly, if I start off with the x, there it is, sitting alone, not a care in the world, along comes the f function. F is going to take x and turn it into something else. But then, along comes the g. G takes that new thing that was created and it turns it back into the original x. So basically what we need to do to test to see if two functions are inverses of each other is take their composition in both directions and see if you actually get x. Let's give that a try in this example. Let f of x be 2x plus 3, let g of x be 1/2 x minus 3. Let's show that f and g are inverses of each other. I'll do one of the directions. Let's try f of g of x. So that is f of, now I'll just plug the g of x right in there. So 1/2 of x minus 3. Now let's plug 1/2 x minus 3 into the f function. F of x is 2x plus 3. So f of anything is 2 times that anything plus 3. So I get 2 times that whole expression, 1/2 x minus 3 plus 3. I will distribute the 2, or actually just multiply the 2, so I get 2 times 1/2, and that gives me x minus 3, but then I still have that plus 3 at the end. Oh, and now look at that, x minus 3 plus 3 equals x, which is great. I started off with f of g of x, and I ended up with x, which is exactly what I wanted. And like I said, I'll leave this to you. It's a similar exercise to show that g of f of x also equals x. Let's find the inverse of a given function. Let's say that I'm given f of x equals 2x plus 3. How would I find the inverse function? Well, there are a few standard steps for doing this. First, replace f of x by y. So you can simply write y equals 2x plus 3. Next step, switch the x and the y. So where there was once y, I now put x. Where there was once x, I now put y. And think about what's happening graphically. This is like that reflection that we saw in the graph. We are reflecting over the line y equals x. Every x and y get exchanged. Now, let's solve for y. So the first thing I might do is subtract 3 from both sides. I really want to get the y by itself. So it looks like it'll end up by itself on the right-hand side. So subtract 3 from both sides. I get x minus 3 is 2y. Oh, hey, look at that. I'm almost done. Divide both sides by 2. And we end up with x minus 3 over 2 equals y. Look at that. I solved for y. And the last step is to recognize that y is your inverse function. And so I can write this as f inverse of x equals x minus 3 over 2. Here's one last example. And I encourage you to pause the video and try this thing as we go, or at least try the steps. As I go, pause and see if you can figure out what the next step will be. All right, let's begin. Here's my function, f of x equals 8x plus 1 over x minus 1. And I claim that it is invertible. Let's find f inverse. What's the first step? Take that f of x and replace it with y. Next, let's interchange x's and y's. And now my goal is to solve for y. And now this is where people get stuck. This is kind of a tough problem to work out if you haven't done something like this before. But maybe we can simplify things by getting rid of fractions and expanding through as much as we can. So to that end, let's multiply both sides by that denominator, by the y minus 1. And so we get x times y minus 1 equals 8y plus 1. And now let's expand that left-hand side. So I'm distributing the x. So xy minus x equals 8y plus 1. And now this is good. I've gotten rid of fractions and I've expanded everything. Let's recall our goal. Our goal is to solve for y. I want y by itself on one side of the equation. I look for the expressions that have y in it. There's xy and 8y. Let's put those two things on one side of the equation and everything else on the other. So the 8y, I'm going to move that to the left. At the same time, this minus x, I'm going to move that over to the right side. So we get xy minus 8x equals x plus 1. So now my y's are together on the left. Well, do you see what we do next? Now let's factor out the y. That'll give me a single y. And there we go. 8 minus x times the y equals x plus 1. And this is great. Since I have a single y, which is a multiple, it's a factor of the left-hand side, now to get y by itself, I can divide both sides by this x minus 8. And there it is. So y equals x plus 1 divided by x minus 8. And that's it. We've done it. Our very last step is to just recognize that my f inverse function is what I had as y. And so that's x plus 1 over x minus 8. All right, and that concludes one-to-one functions and inverse functions.